So I'm going to talk to you guys about the 5 levels of secure hardware. The 5 levels of secure hardware is a thing that I started thinking about a few weeks ago, modeled after the 4 types of ZKVM, the 6 paths, the 6 levels of autonomous driving, the 5 steps to AGI. It seems like when there's something impossible, people need a roadmap for it. And so here's a damn roadmap. I think the TLDR is that I think that the stack is ready to do great applications, and we should now go and fix the hardware and build the great applications. And everybody is really busy, and I think it's important to just cut the chase. So the 5 levels of TEs, or secure hardware, or trusted execution environments, or whatever you want to call it, are these 5 levels. I'm going to get into this in a bit, but I'm going to leave the slide up for the people that are impatient and want to leave the room. Yeah. Okay, so let me get started by saying that the most powerful thing that we're after here is programmable cryptography. Programmable cryptography is a very powerful primitive that people at 0xPark have been memeing recently, and it more broadly refers to using cryptography to enable safer, more fun, and more intelligent experiences. And what do I mean by that? By safer, I mean, we did a demo in August where we collaborated with the Cursive team. It was an interesting group of people that I don't know exactly how to describe, but basically what we did with them is a recruiting safe dating app. Now, what does this mean? It means that at our event, we gave everyone NFC chips as their badges, as their conference badges. And when you tapped on each other's badge, it would open their profile. And ahead of time, you would have configured your profile as if you're a recruiter or a candidate. And if you're a recruiter, you're saying, I'm recruiting for these kinds of people. If you're a candidate, I want to be recruited for these kinds of things and within these salary bands. And well, one could say that, hey, why don't you do that out loud? Where if I go and like say out loud that I'm looking for a job, maybe my boss is going to fire me. So instead, what we did is that we allowed people to connect. And if there is a match during that connection process, privately, it would let myself know that, hey, I met a recruiter. That guy was a recruiter. And if you want, you can opt in to tell them about it. And safety is really important. It's at the core of what cryptography enables. We got asymmetric encryption gave us safety over talking about things. I think here we're starting to see something really extremely powerful, which is that we can create safe experiences by doing set intersection operations over like 2 people talking to each other. And that's extremely powerful. Now, then a few weeks ago, we saw that programmable cryptography actually allows you to do something that's super fun. So here you see the UI of teleport.best.link, whatever you want to call it, with my account, where I can literally add a template to my tweet as a filter, and then I can give anyone this link. And as long as people try to use this link, they can tweet anything from my account, which is, again, pretty powerful. Who here knows about Twitch Plays Pokemon? All right, so this stuff allows you, instead of doing Twitch Plays Pokemon, it allows you to do group chat controls 1,000 TikTok influencer accounts, and they all tweet or cast or TikTok the same thing at the same time, taking over the algorithm. This is powerful stuff. This stuff has not been done before, and I think this is like one of the things that really excite me about programmable cryptography. Doing things that people have told us are crazy, maybe they've told us that they're unsafe, maybe they've told us everything that is impossible. Programmable cryptography starts to make these things really possible, and it's really exciting. The third thing that I'm super excited by is intelligence. And you will notice that the most recent GPUs, the H100s and now the H200s, they have a secure enclave element to them. So not only can we do safe experiences with 2-party computation, private set intersection, not only can we do fun things with things like teleport.link, where you can forget your account to an enclave, now you can actually draw a wire from a hospital database record straight to a GPU. And that's pretty powerful, because that means we can train the next generation of AI models on private data, on data that lives in our chat rooms, in our chat histories, in like all sorts of like sensitive places. And this is what's, in my view, like one of the most exciting areas where people should be spending time on. Notably, you will see that in this abstract, for the majority of typical LLM queries, they all with large models and longer sequences overhead. So that's powerful. It means that the stack today allows us to do things that were not possible before with less than 10% overhead. When you hear about that in the context of FHE or it is much worse. What's up?
Maybe adjust your hand on the mic. You might be blocking the
sound. Test.
Yeah.
Okay, now? All right. Should I go from the top? All right. So as I was saying, sub 10%, whereas what everybody else has told you about every other technology is not sub 10%, it's over 10,000, which is, a big gap. So just to go over the classic thing that people will always talk about, ZK, MPC, FHE, IO, TEE, word salad, what all of these things mean. Well, they are tools in our cryptography toolkit, and they allow us to do different things. I can use ZK, a snark, to attest to computational integrity. I can also use a snark, a ZK snark, to also attest to some private information and make some claims about it. What a snark in a vacuum cannot do is it cannot handle private shared state, meaning that, for example, like what the Renegade project is doing, if like I have some state, such as my order, and Charlie has some state, such as his orders, a snark in a vacuum is not able to allow us to do a private match. But what I can do is I can combine a snark with something else, and maybe I can do a private match over like two pieces of shared information. Now, on the FHE world, where FHE means fully homomorphic encryption, which is a big hammer, and there's like lower things like somewhat homomorphic encryption or additive homomorphic encryption that you can use to do very exciting things. You run into this very interesting problem where once I have encrypted some state, for example, to Mateusz's public key, or to some public key, I can do additions, multiplications over it at a gigantic overhead, but maybe it's like useful. But what I cannot do is that I need to know, I need to read that state. And there is a question of how do I decrypt then? If I give it to, if it's like encrypted to Mateusz's public key, then that's not that useful because he can just take his public key, his private key and decrypt it. And then, all my data is gone. Now, an interesting thing that people do here is that they say, okay, which was the Taurus FHE work that was done recently or like a few years ago, where you take an N of N network and you have that network run the decryption. So now, not only do you have the overhead of a 10,000x or whatever computational, you also have a live network that you're expecting to decrypt your information for you. You're relying in a collusion resistance assumption, and your liveness is garbage because anyone can go down and you cannot do T of N decryption instead, which is not great. In the MPC world, MPC is nice, but it's not really that crazy of a thing because it still requires a T of N non-collusion assumption. And T of N is like a pretty not that robust solution in my view for the things that you want to do here. And also it has massive overheads in bandwidth and computation. And also for the very nuanced readers, it also has like troubles expressing things like divisions like in a very nice way. Now the holy grail of like cryptography, which lets you do everything much better, is IO, or indistinguishability obfuscation, my English. And the problem with IO is that, well, we don't know that it exists. Is the IO in the room with us? Clearly not in this room, and I don't know about other rooms. So, which brings us to the great subject of today's presentation, which is the TEE, the trusted execution environment, or the secure enclave, or the trusted compute element, or the isolated memory region. There's like many names to the thing. But one thing that I really like, and it's like another explanation from our favorite Andrew Miller, which is that TEEs allow you to do things that cryptography alone doesn't, like verifiable data deletion, decentralized front-end hosting, collusion resistance, etc. It's quite interesting to think of the TEE as yet another tool in your stack of programmable cryptography and using it where it makes sense. I can take an FHE platform and I can instead put the key, the decryption key that Mateusz would hold instead to the TEE, which means that, great, I can, instead of like having like to trust the TEE for everything, and you can trust it just for the decryption. So I can use the TEE as a tool to take things that are shaky in some protocols and give them some additional ways to protect me from things. I'm not saying it's something that you need to use for everything. You layer it on with other techniques, but over time, we will start learning how to use this tool in a better way as the developer experience improves. I think one thing I really want to understand is that this stuff is not going away. It's only going to get more popular. Apple, their privacy company, in my view, has TEEs in their cloud. Every phone, who here has an iPhone? All right, every iPhone has a little secure element that might not be secure to run the Flashbox MEV builder on, but it's pretty secure. It's pretty secure against most adversaries. And can also do attestations. Now, what if we're in a world 5 years in the future where that secure hardware is actually much, much better? What if I can do attestations to Face ID or to an iris scan? That starts to get pretty exciting in the world of identity. The WorldCoin project is like looking into that. So there's a lot of things that are seemingly really powerful that are just hard to ignore about the traction that the TEE platform is. And I think there's like three real ways to evaluate the TEE. Is it fast? Is it easy to use? Is it reliable? And will it not get broken by a guy called Dan? I think it was Dan, right? The guy that keeps breaking the TEEs. Yeah. So on the performances, does it run fast? Meaning, what's the overhead? We saw that the overhead is starting to get pretty good. The developer experience is how much code do I need to think about changing? And the security model is, okay, is it actually a TEE? Or for example, we had a talk from Nitro, like Nitro, for example, lacks some elements on like what really makes a TEE, like can like go and read the memory if I like literally go and plug 2 voltometers on it. The TCB is an interesting angle to evaluate, meaning how much code am I importing for the operating system, but also how much code am I importing from the application layer? Meaning if I'm importing like even if I'm importing libc, it might be too much of a thing. And thirdly, the hardware software supply chain, which is I didn't finish the bullet, but it's basically how much is the hardware open source, if at all? Is the software it's running on open source, if at all? What about the instruction set, and so on? So there's these 3 axes, which brings us the first slide that I showed you in the beginning for now with some context. And I'm going to spend a few minutes walking through it because it's quite dense and it's intended to be so because I think things nice. So how I conceptualize things that we started with the CPU enclaves, right? The CPU enclaves, for example, are the ones that you would run on the Fortanix platform. A year and a half ago, I did a project called Revum with Andrew Miller, where the idea was that you took REVM, the EVM that runs most of Ethereum today, that also powers the Reth project, and you put it in an SGX by literally using the Fortanix platform, which says cargo build instead of target default, you would target the Fortanix SGX instruction set. So that thing works. It's quite exciting. It's quite shocking that it works, honestly. But the developer experience is quite hard. What this means is that I need to think really hard about the boundary of getting information into my program over a TLS connection. I don't get attestations out of the box. I need to think a lot. And if I Now, the main use cases I have seen for this style of thing, as far as I can tell, one was Oracle's way back when with the Towncrier project, and also bridges like the Avalanche SGX bridge that was running for a long time. And honestly, many of these approaches, they were considered garbage for a long time. I think many of these people that took early bets might start getting vindicated. The performance of these enclaves is pretty good. You don't really see any real overhead for the CPU-bound things. But the developer experience, as I said, requires rewriting your thing. Now, across the first 3 levels, you will see that the security model of the thing stays the same. And the security model is pretty bad. It's proprietary hardware and proprietary software. The hardware supply chain is not verifiable, and for all I know, is backdoored. The software is running on proprietary x86 instruction sets. They're really fast, which is why we can get to have this performance. But it's, again, proprietary and not something that you can really work with for global scale. And I think one thing that's really important, and I think we should go and like call all our cloud providers and like pressure them, like people call their senators, we should call Google, like, well, good, we are in the Google office. TE should be able to say which cloud, the TE should be able to say, I am a machine of this version running this program binary, and on US East 1 on this rack, you know, the measurement can go pretty deep. I think it's really important for the TE to be able to attest to where it's running. Because when you know where the TE is running, then there's a security model popular on Twitter, which we've been calling the guy with the Glock security model. And the guy with the Glock security model very simply says that instead of you trusting that Dan is not going to be over your TE to like go and measure it and go and screw it up, you trust that the TE is in a data center with real doors, real people with like security, and they secure your TE on top of any of the hardware security. Or in space, yes, space TE is like, you name it. Nice. So my point being that the cloud TE is really damn important because it lets you know where the device is, and if you know where the device is, you believing that the device is actually secure becomes much more palatable, much more believable. Now that was level 1, and the security model I'm going to get back to when I get back to level 4, but I want to like really communicate the security model here is that we don't have the cloud TE at the station. I think it's really important that we get to it. All right, level 2 was brought, in my view, forward by the Grameen project, where what Grameen does is that it says, okay, instead of you, my friend, having to go and like figure out what the guest host isolation boundary is and you having to rewrite your application, I'm gonna do it for you. And what the Grameen project says is, I'm gonna look through all of your syscalls that go normally to normal clear text, let's say, and I'm gonna rewrite them into confidential syscalls. Like, excuse me for abusing the language, but roughly what the Grameen project does. It goes and edits your compiled code, and instead of it running the native stuff, it figures out how to go in and out from the enclave. But well, if it goes and rewrites and like starts to go in and out of the enclave, well, maybe my code is not actually that optimized for not going in and out of the enclave, which translates into performance overheads. Which means that using the Grameen project is really useful. The teleport demo was written with Grameen, but it's not useful if there's going to be a lot of context switching. If there's going to be a lot of context switching, if you're going to be hitting a lot of these like in and out of the enclave calls, your software is going to be slow. So this actually happened. We found out the hard way when we were building the mevgeth prototype, or the original mevgeth builder running in SGX with Grameen. And then when the Flashwood team started to use the mevreth builder, what happened is that they run on another edge case, which was that not only would it have been slower because of the massive syscall overhead, but what would also happen is that Reth uses MDBX, which is a database that uses memmap, and unlucky, memmap is not supported by the Grameen syscalls rewrite. So what do, right? Like so it seems like Grameen on level 2 gave us the start to build things, but it didn't quite get us there. But it did give us teleport, which took over Twitter, my Twitter for sure, and maybe others. Now, I think we're at level 3 today. Very exciting place to be in. We could stay in level 3 for the next 3 years, and I think we wouldn't be able to do all the interesting applications that level 3 gives us. So I think it's really important that people go and like really hit level 3 application layer with like everything that they can, no matter how dumb it feels. The 2 examples for level 3 are the very recent Intel TDX platform, which has been getting rolled out across major clouds even more. I know that like some of our bare metal providers have them. I know that GCP has them. I know that probably every cloud is going to have them on a wide enough distribution. And also the H200 GPUs that I mentioned earlier. These 2, they work in a different way from how things worked before. Instead of being the app level enclave, it's a full VM. So what you do is that instead of doing cargo build target, what you do is Docker build. And that starts to make things much easier, because now I can start running my containers as I would run them on my Kubernetes cluster, but instead of putting them on a public cluster, I run them in a secure cluster. And the secure cluster is kind of nice because it has attestation support. It can just run things that I would run on Kubernetes. There's one exciting project that built abstractions over that called Constellation. And it was quite interesting because it doesn't require any modifications to my code. I can take my code, I run in a VM, that's great. Now, for the people that have worked with Lambdas or VMs like Firecracker, you would know that the biggest issue with all of these things when developing is the feedback loop between bringing the VM up and down. It's kind of tiring to go and do Docker build, tear the VM down, to bring the VM back up, deploy the app, like go forward. So that's kind of tiring. And like when I spoke with Andrew Miller about this, actually, he said that's why I really like developing on Grameen, because I just cargo build and I hit the ground running and I'm good. So where we are at right now on level 3 is that we can do really crazy stuff. We can do confidential building, like the Flashboots team has been doing recently. We can do privacy preserving machine learning. We can do distributed machine learning, where I don't need to trust that Mateusz sent me the right gradients during his training run. And I can do that pretty well with less than 10% performance overhead. What's the trade-off? Well, it's that little point on developer experience where I need to bring the VM up and down, and that's kind of tiring. Well, we know developers, and we know how to like tailor solutions to developers. And I think it's really important for people to realize that if we can fix this developer feedback loop, we got something super exciting, and I think people should spend all of their energy on it. There was a project that was deployed again by Andrew and then by other friends called DStack, and I think spending a lot of time on what's the, quote unquote, foundry for TEE's UX look like, I think that's gonna be epic, and I think people should spend a lot of time figuring that out. Okay, so just to summarize so far, I think the stack is ready to build great TEE apps. We have had some success in recent times. I think the things that will really work are gonna be super crazy and hard to predict. Who would have thought that I'm gonna be forgetting my account into a program, and that program is gonna be tweeting from me and it's gonna be able to follow rules in a very credible way, etc. It's like kind of interesting. Now, if you go to how do we go beyond that, I think the obvious areas that like keep getting unlocked here are like more global distribution, because people need to trust this hardware. And so far, yes, the app layer is unlocked, but like going and like for Twitter toys, it's good. Maybe for TikTok toys at global scale, it's good. But if I want to like go and like really and sell this to a hospital, it's not really good enough yet. Or if I wanted to like go around the world's identity system on it, it's also probably not good enough yet. Which motivates us to think what's beyond where we are today. And I'm calling that OpenTE, or we've been calling that as a community OpenTE, where it starts with actually a project that I learned very early on in my career called Keystone, where Keystone is a project started in Berkeley, I believe, which was about doing an open implementation of a TE, open software, open hardware on RISC-V, blah, blah, blah. Now, what's hard about going from L3 to L4 and L5 is that anytime you try to do something more verifiable, more decentralized, more anything, you lose all the benefits that the proprietary players have, which is that x86, really fast. RISC-V, not that fast yet. Is it gonna get fast enough? For sure. When? We need to accelerate that. So we need to spend more time getting the RISC-V instruction set to be really, really fast, because it's a credible alternative to the most powerful microcode architecture that exists today. Now, that's on the software layer, how do you get like good instruction sets. And on top of that, you need to do attestations in an open way. I think, I'm not an expert on that, but I think that is tractable. It seems like there's enough bits and pieces of open source technology here and there that we can use to do open source attestations. Now, the hardware thing is the really interesting thing here, which is that if you get verifiable manufacturing, that's pretty exciting, but how good is your hardware going to be? And even if you do get verifiable manufacturing, again, is your hardware going to be compatible with or as good as like what all of the proprietary guys are doing? Again, I don't know, but it seems like a very interesting area to go down to. Now, what's missing from L4 is that even if it's fully open source, fully auditable, near good performance, it's missing one thing, which is redundancy. It means that you're still vulnerable to the classic hardware attacks that people keep coming over. Secure hardware is not secure, as one would say by definition, because somebody will find a way to break it. Well, okay, what if I did a cryptographic computer with multiple pieces of secure hardware and had each one of the secure hardwares talk to each other? And yeah, maybe one fails, but at least I got like a 2 of 3 attestation, and that's good enough. And that's L5. L5 is basically multiple heterogeneous TEs, ideally by separate manufacturing processes. It's kind of like, you know how Ethereum is like built with client diversity in mind because it increases the system's robustness? People would argue that like maybe that's an anti-feature because it slows down development or it makes the whole system slower because you need to accommodate for the slowest node. But my claim would be that for true things, real global scale, you need something like this. You need to think really deeply about how redundant your stuff is. And in this case, I think a true cryptographic computer requires multiple TEs talking to each other. Ideally, we can print them on like one PCB so that they always like talk to each other. And if I were to predict, like, you know, like 20 years in the future, how do we do computation on the internet? I think it would probably look something like that. Now, there are trade-offs. It's very exciting. We can get there, but there's trade-offs. Anytime we improve the developer experience, the TCB grows. What does this mean? It means that like in the Gramming case where you're importing a bunch of stuff in your code that like does stuff for you, anytime you import an abstraction that makes things for you, it means that it's a source of risk. As I said earlier, the open source instruction sets may reduce performance, which I think is navigable, as we've seen by the collective genius of the open source world, but we gotta get there, and we're not there yet. Improving the TCB can be done with like minimal operating systems like the Yocto project, but who here has like read about the Yocto project or knows about it? All right, well, you guys all know how bad it is, and no. And we can do prototypes about these things all day, but like getting to something like, you know, global scale production deployment is a big gap. And obviously for L5, I think redundancy comes at a cost, and it's TBD whether that cost is going to be navigable or acceptable. So let's do it. I think we can do it. We have to fix the dev tools. I would love to talk to people thinking about D-Stack style dev tools. I think everybody should call their cloud providers and like bully them basically into adding the right level of attestation. And if they don't have them, they should say, I'm going to go to your competitor who's going to add it. I think we should figure out the open source manufacturing process. I think that there might be exciting steps there. And finally, I think we should invest in better open source ISA performance and making RISC-V epic. Okay, that's it. Great. And do we have time for questions or?
How do you trust the TE when it's attesting where it is? Like it says, like I'm in this subnet zone, and someone it's how do we trust that?
Yeah, I don't know.
Oh, yeah.
Yeah, seems important.
You're trusting a key. You're trusting the key of the manufacturer. Because the attestation is signed, so you can check the signature with a public key, and the public key is tied to the manufacturer. So right now, you're really trusting the manufacturer as well. So for the future, for open TEEs and all that, what we want to try to get to is
that you trust if you want a verification process of the hardware, and then there will be a public key tied to that verification process. But in my opinion, the remote attestation challenge is really, it's the toughest challenge of everything we need to do moving forward. Because to go back to your question, right, you're talking to a remote machine, and it needs to prove to you that it is what it claims to be with respect to both hardware and software. So the challenge is really, really non-trivial.
Yep.
Yeah.
Wait, can I ask a follow-up? Why do you care about location? Like physical location? Is that what you're asking?
Yeah, like physical location.
Why does that matter to you?
Well, because if the TE is like sitting right here,
Yeah.
you can go and play with it and try to screw it up in like any ways that you want, as much as you want. Where if you can convince me that the TE is a data center with like 10 guards, I can trust that a little more.
One last question, Georgios, so you get to pick.
Hands?
The man with the Glock theory. Yeah. The man with the Glock theory is basically like we're inheriting the physical security of the location, right? So would you say if we just put like validator nodes in museums that already have paid security and 24-hour surveillance, that would be like effectively the same, right?
That would be epic.
Okay. It would make sense for the museum to get the yield.
Yeah,
Yeah.
museum, home staker, all of it. Right. But my local museum in Greece does, so maybe, yeah. All right, thank you all.
Awesome.